Welcome to Matsci Afterclass. In this video, we're going to reproduce and then discuss a famous experiment which is called the Rupert's drop. A Rupert's drop is essentially a piece of glass but in a very special shape, the shape of a droplet. Or say it looks pretty much like a tadpole with a very round head and a very thin and long tail. So what makes this interesting is that its resilience to fracture strongly depends on which part of the body you apply the force to. This is a hundreds of years old experiment, so there are a lot of articles and videos online. So make sure you check them out if you want after this video. Now let's see how we can make a Rupert's drop. So basically you need a piece of glass and you need something to melt it. Glass is not something particularly difficult to melt, but for this you will not be able to do it with your stove top, for example. You will have to use something like what we show here in this video because you need to mix it with oxygen to help it burn at higher temperature. Like the torch here we show in this video, we used regular propane, but its difference is just we fill it with oxygen, so the flame temperature can go actually can go well above 1,000 degrees Celsius. Some of you might have a torch at home. Those are probably bigger and longer and usually used for welding or cutting metals. The fuels you use probably is a different fuel. It's acetylene, which can burn actually much hotter than this propane torch we show here. Another possible way to do this at home is if you go to Home Depot, you probably can buy those butane canister with a torch head. Those can definitely burn hotter than the stovetop. Although I've never tried to use that, so no guarantee it will melt a piece of glass. Now the bottom part begins to melt, forming a blob under gravity and gradually separated from the rest of the body. And eventually it forms droplet into the water. Okay, we'll play this at a faster speed as Xudong, who's doing the experiment, is trying to make a second drop for us. So the tricky part here is as the head separates from the rest, you want it to get into the water as quick as possible, but at the meantime you want the tail part to be just hot enough so it gets deformed and stretched, forming a long tail. Now let's put this to a test, first on the head. I'm not sure why this is done on a piece of dirty sandpaper. Shudong is trying to convince us by hitting it multiple times with a hammer. Because of the way the drop is put on the table, you can't really hit it much harder than this because that will bend the tail. And you're not supposed to bend the tail. Alright, now it's pretty clear that it has a very tough head. So let's see what happens to the tail here. Pay attention to the head as we snap on the tail. So the whole thing just shattered even though we're not doing anything to the head. It's not difficult to understand why Rupert's drop has such interesting behavior. Let's imagine this melted, very hot piece of glass gets into the cold water. We know glass is not a good conductor of heat, so we can imagine the outside layer will cool down and turn into solid first, and this will slowly move into the inside. Using this picture here, we have the outside a blue layer, meaning it's a cool solid, and in the middle we have the red part, which is a very hot. When the liquid turns into solid, its volume shrinks. So if we imagine the middle layer, which is the yellow layer, as it cools down and turns into solid, it will pull the outside layer, the blue layer, which is now a solid, it will pull it inward, introducing compressive stress in that layer. And also because this is a droplet, which has a large head and a small tail, so the temperature gradient in the head is much greater than that in the tail, which translates to a larger compressive stress in the head part compared to that in the tail part. Now, this might have reminded you of something we learned in class under the topic of failure mechanism. So I bring this slide from class. You might remember one way to improve the fatigue life of a part is by introducing a compressive stress on the surface of material. For example, this is done through the shot peening. And actually, this is not only for fatigue life, it applies to tensile strengths and fracture toughness as well. And if you prefer some more exercise, you can ask yourself what leads to fracture, which is the crack formation and propagation, and what leads to that is a plastic deformation, or say the dislocation movement. Now come back to this Rupert's drop. It's no wonder we cannot break it on the head because it's under a large compressive stress, so it's much strengthened at the head part. For the thin tail, because the compressive stress is not as strong, and also because the size is smaller, it's actually possible to break it from the tail part. Now remember, the drop is cooled from outside to the inside as a whole, which means the structural integrity is very important. If one part breaks, the enormous stress within each layer will no longer be balanced, so the whole structure will shatter. Now we've demonstrated the experiment and we discussed the physical origin. Normally this is where an educational video would stop. But since the purpose of this video is to complement our learning in class, I'd like you to take a few minutes to think of the factors, or say the material properties that makes glass the material of choice for us to do this experiment. Now, pause this video, give yourself a few minutes. When you think you've got an answer, click play again, and I will share with you my thoughts. Okay, I think there are a few factors, more than one, that are equally important for glass to be the material here. The first factor is a low thermal conductivity, which means you can have a large temperature difference across the material. The picture shown here is just to make this presentation more interesting. Well, the material is not glass, it's a different porous composite material. Anyway, when the melted glass meets water, so the low thermal conductivity allows it to cool down one thin layer at a time. And this is important because that thin layer allows enough flexibility and also allows a relatively high stress level. If otherwise we have a high thermal conductivity material, that means the cooling will happen much faster, so a very thick layer will become solid at the same time. So the stress in that layer won't be as high as in the case of glass, and also the deformation won't be enough to accommodate all the volume change. In fact, if you cast a piece of melted metal into water, more often you will get a porous structure. So as the liquid solidifies very fast, it forms pores. Now you might feel confused because low thermal conductivity and high cooling rate sounds like a recipe for disaster. Just like if we put a hot glassware into cold water, it will shatter, right? But this is not what's happening in this Rupert's drop experiment. That is because the cooling happens from a melted liquid state to a solid state, and it only solidifies in a very thin layer at a time. So as it's thin, the glass is actually flexible. A good example for flexible glass as it's thin is the optical fibers, which we use for telecommunication. In the end, a large amount of stress is stored in this glass structure. The second factor is that glass is an inorganic material made of covalent bonds. As we learned in class, covalent bonds are rigid,
they're directional, and they are hard to deform. So with this kind of bonding, the materials are usually strong, but they can't deform easily, especially under stress. They can form dislocation motion, they can form slipping or twinning, the common mechanisms for material to relax under stress. So you can imagine in this case, if we have a metal or a polymer, they will be able to relax under stress through deformation. This means, number one, they can store a large compressive stress in the structure. And number two, when one part of the structure is broken, so that means the balance of stresses at different places in the structure is broken, the structure can quickly adjust to that by relaxing and reaching a new balancing configuration through deformation, so the whole thing will not shatter. As an extension to factor 2, the covalent bonding makes glass a strong and brittle material. So the high strength plus the further strengthening given by large compressive stress give it a very strong head. And on the other hand, the brittleness make it shatter when the structural integrity is broken. The last factor, as indicated by this screenshot, is that the large temperature drop when a melted glass go into the water. That allows more compressive stress to be stored in the structure after it solidify and cool down to the room temperature. In the end of this video, I have one activity and one question for you. They are optional, but if you try them out and write a brief report, less than 1 page, I would be happy to give you bonus points in class. Okay, here is the activity. I would like you to try out the Rupert's drop experiment with a different material that you can find at home. One example is you can use sugar, which you can melt on stovetop and then pour them quickly down into icy water. Of course, you can choose other materials as well, for example, wax. And in the end, you can report how the experiment went. Can you reproduce a Rupert's drop kind of behavior? What do you think the reasons are? And that will be enough. And for this question, I'd like you to pay close attention to this video recording here. Notice the tail of the drop in this video. Notice a few seconds ago, like in this video here, this drop actually had a very long tail, but that was gone. At this point, it's broken already. Wait a minute, it's broken, but the entire structure didn't shatter. I want you to think of why this drop didn't shatter when that long tail broke, and just write a few sentences about it. Alright, that'll be all. I hope this video and the bonus activities will help you learn better the topics we covered in class, like strengthening mechanisms, strain and stress, failure, as well as the relation between bonding and the mechanical behavior of materials. Alright, thank you for watching.